right, good morning, everyone. There's a few administrative things to take care of really quickly. First, thank you for everyone who turned their tests and assignments in. I will be getting those graded. What I have to do on them is go read through all the essays and give you your score on those. So currently your grade is showing as lower than it will be once I finish grading all of the essays. A look ahead at when your next group of assignments are due. So let's go to the assignment area. You'll see that your next set of assignments will be due on March the 6th. So that will be homework assignments number 4, number 5, and number 6. Also, your test number 2 will be due that same night. So once again, there are 4 total things that you will need to have done, and there are 4 weeks to do them. Please remember they're due at 11:59 p.m. Eastern Standard Time, and at 12 a.m. this morning here, like they all just completely closed down, right? Anything that you turn in after that, it won't accept. So please make sure you get those done on time. If you have questions about them, you can always ask me at the beginning of class or send me an email, and I will try my hardest to get you a good answer. So just take note of when those are due, and they are available for you now. All right. As far as journals, just want to make sure everybody can see in the journal section. Journal entry number 5 is available. For those of you who still aren't sure how to find this information, the reason for these is to hopefully send you down a rabbit hole of astronomy discovery. So this asks about the giant impact hypothesis. If you Google what is the giant impact hypothesis, it will pop it out. It says, do you agree with problems with the theory? Why or why not? So just give me some ideas with how you're feeling about it, what you think about it. Does it seem realistic? And I'll get those graded for you. All of the current journals, I believe, should be graded. I'll go back in and check. And just remember they're due every Friday night at 11:59 p.m. Eastern Standard Time. Last reminder for the day, don't forget your lunar observation calendar. That is due on Saturday, May the 1st at 11:59 p.m. Eastern Standard Time. There's a description of it here. There's a moon sheet here if you want to print one off. If you need me to get you a copy, just ask me. I've got some extra physical ones I can just hand to you. A question that I often get is, Mr. Palmer, what if I can't see the moon that night? Figure out how you can make yourself see the moon that night. I don't want to give like tips and tricks of what you can do, but you can find it. You can figure it out. You just got to put the work into it. I doubt there's going to be 28 clear days where the moon is just like beautifully available for you. So figure out how can I view how the moon looks today if I'm not able to physically see the moon. You don't want to take this shortcut all 28 days because you'll cheat yourself out of the experience. But if you got to do it, you got to do it. Okay. One last thing. Don't forget all of your lecture slides, are visible for you. Let me make sure this one's in the right place. All right. All your lecture slides are available for you in the lecture slide section. Great. And lastly, in the lecture video section, there will be a video lecture twice a week that I will upload. There's the one that you will experience, which is on Tuesdays. And then day 2 is Thursday's lecture. You won't be in class for that, so please make sure and check out at least the day 2 videos each week so that you can see what's going on in class. Before we get started with the lecture today, does anyone have any questions, concerns, comments, or complaints? Awesome. If you think of something later, feel free to email me. You can always call me at my office phone number, which is on the syllabus. I am available to help. All right, let's do it. So today we're going to start in chapter 4, which is making sense of the universe. We've already found our place, quote unquote, in the universe. We have discovered the universe for ourselves, talked a little bit about the science of astronomy. So now we want to start working towards making sense of everything. And of course, we're going to start, just remember, the geocentric model. This is a rough approximation of the model. It basically says the Earth is the center of everything. So everything must orbit around the Earth. Either it's on Earth or it's in orbit around the Earth. Of course, there's also something called the firmament, which is the space slightly above the Earth, but everything else orbits around the planet. I want to talk about Galileo Galilei today, as he did a lot of work to just destroying the idea of the geocentric model. As stated, he was one of the first to turn a telescope to the sky. Now, when I say a telescope, at the time they're often called looking glasses. Sometimes they were used to look over the ocean to see if enemy ships were coming, or maybe to peek across town. But he was one of the first to use it to look at space stuff, if you will. He also used it to look at the moon, and one of the tenets of the geocentric model is that things on Earth could be interesting, but everything in space was just a light of some sort. So when he viewed the moon and noticed that the moon had features such as peaks and valleys and mountains and craters, this was a big problem because the moon was in the celestial realm and therefore shouldn't have any of these qualities that you would find on Earth, right? You know, mountains are on Earth, valleys are on Earth, but then we're seeing all these mountains and valleys on the moon. That's a big problem for the geocentric model. But Mr. Galilei wasn't done with that. He kept detailed observation records of his views of Jupiter. Now, I've viewed personally quite a few things through a telescope, and none of them is as interesting looking as Jupiter. Sure, Saturn is pretty, it has nice rings, but when you look at Jupiter, you always see from 2 to 4 of these really bright stars that are around it. And if you stare at it for 2 hours, which it's easy to do because it's so enthralling, you will be able to see these stars moving relative to Jupiter. They're always in orbit around Jupiter. So you can see from his observation record, this night we got a Jupiter, we got 2 of these stars. And then we got 2 of these stars and then a third one. Then we got 2 of these stars and a third one. And he was able to plot the orbits of these quote-unquote stars as they orbited around Jupiter. Of course, he eventually knew that they were moons of Jupiter, showing a clear example of things that orbit around something other than Earth. Again, geocentric model says everything must orbit around Earth. This shows that that is not true. This in itself should have killed the geocentric model, but people weren't quite ready to give it up yet. He also observed the phases of Venus through the telescope. Okay, so whenever you view a planet or an inferior planet from your perspective, and inferior just means closer to the sun, so whenever from your perspective you view an inferior planet, it will display phases. So as he's viewing Venus and he sees these phases, this tells him this thing is at least sometimes closer to the sun than I am, or than my perspective. He also noticed that during its thinnest crescent phase was when it was its largest. during its nearly full phase over here, it was at its smallest and dimmest. This tells us that this object is closer to the sun than we are, but when it's in this phase, it's closer to us than it is when it's in this phase, which could only occur if it's in orbit around the sun and not just the Earth. Again, the geocentric model should be done at this point. This is just a small slide showing the different possible phases based on where Venus would be relative to the Earth if the geocentric model were correct, or if the heliocentric model is more correct. You see here the order of the phases. So again, geocentric model. Of course, during this time, the group in power was dedicated to keeping the geocentric model in place, since that was the belief structure of the current political power. I'm being as politically correct as I can. Since this was the belief structure of the current political power, going against the geocentric model was bad for Mr. Galileo's career, and he was forced to recant, and he did not recant his recantation until he was on his deathbed, when he was just like, oh, BT dubs, the heliocentric model is correct, check my observation journal, have a nice life, and then he died. Which is humorous, but also pretty sad. So good discoveries, Galileo's awesome. This is why you often hear his name when it comes to astronomy. Another person we don't talk about quite as much as far as astronomy, but in physics, you'll hear him all the time. In fact, we've got a branch, Newtonian physics. Isaac Newton, Sir Isaac Newton, if you will, in the 1700s, he wanted to describe how things moved. Now, all the way back here, Johannes Kepler had come up with some laws of planetary motion, but Isaac Newton was like, no, I want to take that a step further. I want to describe how everything moves. So let's look at Newton's laws of motion. Law number one, law of inertia. Seems pretty straightforward, but we want to state it anyway. It says a body at rest will stay at rest, and an object in motion will stay in motion at a constant velocity, straight line, unless acted upon by a force. Now, this seems pretty straightforward. However, it also gives you a definition of what a force is. This says that a force is something that changes how a thing moves. And a thing should just be sitting there, unless something causes it to move. And a thing that's moving should keep moving, unless something stops it. This tells us so much. Here's the ball, camera, here's the ball. I'll put it on the table. The first law says that that ball should not move or start moving unless some force makes it start moving. And lo and behold, it does not seem to be moving. It's not going to start moving, I don't think. Awesome. But I'm going to apply a force to it, which makes it move, and it starts moving. Awesome. And eventually it'll stop rolling. And if it stops rolling, well, that's not it moving at a constant speed, so something must be slowing it down. Okay. So I want you to just put this one, the law of inertia, in the back of your head somewhere. This is going to play in a lot what happens over the course of the next few lectures. All right, I got a very brief video that hopefully plays correctly.
But what would it take to launch a cannonball into orbit? When the famous British physicist Sir Isaac Newton saw the apple fall, that some say hit him on the head, it changed the world.
tree. And he looks up and sees the moon in orbit around the Earth, and judges that not only is the apple falling to Earth, so too is the moon.
But could the moon really be falling?
Oh!
By thinking of a cannon and the trajectory of the ball it shoots, Newton used math to unlock a cosmic mystery. It came in his landmark publication, Principia Mathematica, in 1687.
I think it is a famous drawing. And in it, he draws a planet and a little mountain. There's a little projectile first kicked off the mountain and it falls down a little bit. You give it more speed, it goes a little farther out.
We're now saying you could just increase the force all you wanted. It could go 50 miles, it could go 100 miles before it fell.
By adding more gunpowder, and with just the right angle of fire, a cannonball can be made to go faster and farther. Inevitably, however, gravity wins, pulling the cannonball back down to Earth.
The Earth is round and not flat. So Newton realized that if the cannonball is fired at sufficient speed, the cannonball would actually go into orbit.
For that to happen, Newton determined, the ball would need to be shot out of the cannon at 17,500 miles an hour.
It starts curving around the Earth, and he realized that there must be a speed where it goes completely around the Earth and hits you in the back of the head, never actually hitting Earth's surface. And if you duck, it'll just keep going, and lo and behold, you have an orbit.
But why doesn't the moon fall to Earth?
The moon also has some sideways motion. So for every little bit that it falls down, it also moves off in this direction, and the sum of all those motions is an orbit around the Earth.
Newton also realized that the Earth is in a giant free fall around the sun. With gravity forging the path, our planet rounds the sun like an endless cosmic roller coaster ride. Newton cracked the gravity code, and physicists are still using his ideas to solve all sorts of problems.
Alright, so I just like to show that video, well, one, because it's interesting, and two, because that relates Newton's laws of motion to Kepler's third law of planetary orbits. So I just like to relate those two really quickly. Okay. So just to recap here, very briefly, it just says that as you shoot something horizontal to the surface, it's going to fall to the ground because of gravity. And of course, the faster you shoot it out, the further it will go before it falls to the ground. And the idea is that if you can shoot it further and further, eventually the distance that it would travel before it falls to the ground is equal to that of the circumference of the Earth, so it never actually falls and hits the ground. Now you might be thinking, but Mr. Palmer, what about the atmosphere? That's true. The atmosphere will slow the cannonball down so that the cannonball on the surface would never actually go into orbit because it won't be able to keep that horizontal velocity. However, just a few hundred kilometers up, and the atmosphere is 0 to near 0, and therefore you could put something in orbit like an International Space Station. All right, let's talk about Newton's second law. This is the one most often thought of when you talk about Newton's laws of motion. In its simple form, it says that the amount of acceleration that a force produces depends on the mass of the object being accelerated. I don't really like putting it like that, so I'm going to write it a different way. And I'll move. I usually think in order to accelerate a mass m at a rate a force F must be applied. So what this equation says is that if I have an object with this mass and I apply a force of this size, the object will accelerate at this rate. Pretty straightforward. Now, this is a simplified version of it. This assumes that the mass stays constant over time. And for, I don't know, 90% of objects, the mass is going to stay constant. But when we start launching rockets, we have to understand that the rocket is going to lose mass as it goes up because it's spitting fuel. So we have to write the whole equation instead of the approximation part of it. We're not going to do quite as much with this one, but I do want it to be in your notes somewhere in case we have to use it. All right. Sir Newton had one more thing to talk about. And before I go to that, I just want to make sure and clarify how smart this guy was. He created calculus. He wrote a book, Principia Mathematica, and in this book, he's like, I'll just create an entire new branch of mathematics, which on the surface is super hard, but once you start utilizing it as a tool, it makes stuff easier to understand, which is kind of difficult to grasp in the first place. So, hats off to someone who can create a type of mathematics. All right, let's talk about the third law. The action-reaction law, which I think is the one that's most commonly misused by folks, it says whenever one body exerts a force on a second body, the second body exerts an equal and opposite force on the first body. Which creates an idea that I call force interaction pairs. Basically, if a force is going to act on a thing, there must be a thing for it to act on, for lack of a better term. If you're going to push on the wall, then the wall also pushes on you. So there's always at least two things involved in a force. So I call them force interaction pairs. But the best way to think about this is people usually say for every action there's an equal and opposite reaction. Okay, that's true, but let's think about what's happening. So I push on the wall with 8 newtons of force. The wall must push back on me also with 8 newtons of force in the opposite direction. If I pushed on the wall and the wall did not push on me, I would just phase through it, which is not what happens in our reality. If the wall is not structurally able to put that much force on me, then I will just break through the wall and I'm no longer pushing on it, right? But that's not the wall not pushing back on me. That's the wall attempting to push back on me until it actually crumbles and then my hand just goes through the air where it would be. But Newton's third law also creates some really interesting situations that I want to talk about. And for that, I will bring back out my racquetball. Okay, everybody see the racquetball? Now I'm holding this racquetball up here, and it's not moving. relative to the surface of the Earth. If I let it go, what's going to happen? Sure, it's going to bounce, but first it's going to fall downward, right? Okay, so if it is not moving at all, I let it go and it starts to fall, that means that a force must be being applied to it, right? A force that causes it to accelerate downward. Awesome. We know, or we call that force gravity. And we know that gravity is being applied on the ball by the Earth. Pretty straightforward. However, we have to remember force interaction pairs. If the Earth is pulling the ball downward with a certain force, the ball must also be pulling the Earth up that same amount of force, right? Which is really weird to think about. Now you're like, how come the Earth doesn't move? Well, it's huge, right? If you look at the Newton's second law, F equals ma, if the force is the same on the ball and on the Earth, the ball has a small mass, big acceleration. The Earth has a giant mass, small acceleration. But it's really interesting to think of that just as the Earth is pulling the ball downward, the ball is pulling the Earth up the same amount of force. Not same distance, just same amount of force. Pretty exciting. So I want to use that to move into the universal law of gravitation. Universal law of gravitation. This describes the force of gravity that any two objects will put on each other. Once again, you'll notice the universal law of gravitation describes gravitational interaction betwixt two objects. It says first, it equals the force that object 2 puts on object 1. There's that equal and opposite force we're talking about. And they're both equal to a value that we call the gravitational constant, big G. And that's times the mass of object 1 here, times the mass of object 2 here, divided by their distance from each other, squared, r squared. And specifically, it's the distance between their centers of mass, but using this setup, we can find the force of gravity betwixt any two objects. Please make sure you have in your notes somewhere the gravitational constant of 6.67 times 10 to the negative 11 Newton meter squared per kilogram squared. Those units are hilarious, but important. One of the examples I did in class with this yesterday is someone was like, hey, I want to find the force of gravity betwixt the Earth and I. So we spent some time working that out. It's pretty cool. All right. Wait till everybody gets this written down, and we'll look at that. So the mass of the Earth, which we're going to call big M, is approximately 5.94 times 10 to the 24th kilograms. The gentleman's mass that we were looking at yesterday, which we'll call little m, was about 81 kilograms. And the distance from him to the center of mass of the Earth is going to be approximately the radius of the Earth. So that's going to be about 6.53 times 10 to the 6 meters. So 6,530,000 meters approximately. So using the universal law of gravitation, we should be able to find the force between he and the Earth, and possibly even find his acceleration due to Earth's gravity. We'll set this up, and this is just me showing you an example of what can be done with this universal law. The force of gravity betwixt he and the Earth. Oops. So big G M R squared. Nothing weird so far. That's the mass of the Earth multiplied by the gentleman's mass. Awesome. So this should give us some value. It's a force. And I did this yesterday, but I'm going to calculate it again just to make absolutely sure that I'm not making any mistakes. Well, I got a slightly different value because I used different numbers, but it should be all right. All right, so the value I get for the force of gravity is equal to approximately 762.6 newtons. Now, you might be thinking, what does all that mean? What is 752 newtons really? Again, this is the amount of force. The unit newton can be written as a kilogram meters per second squared, which means that it can accelerate something with a mass of 1 kilogram, 1 meter per second squared. Or in this case, something with a mass of 752.6 kilograms, 1 meters per second squared. So that often helps people understand what it means physically. But I want to look at another thing really quickly. We know that F equals MA. So if I have an F and I divide it by the mass, I should be able to find the acceleration. So if I divide this value by the gentleman's mass, I should find his acceleration. Just as if I divide this value by the Earth's mass, I should find the Earth's acceleration. And again, this is just me showing you an example. So I'm going to take that force and divide it by the gentleman's mass, which should give me his acceleration. And it's going to be slightly off because I didn't use the full value of that or that, but it'll be close enough. You get approximately 9.29 meters per second squared, which we know the acceleration to the Earth's gravity is approximately 9.8 meters per second squared. So I'm all right with this because I know where I messed around. This tells us how fast he can accelerate towards the Earth. Oops. On the other hand, I can find out how fast the Earth is going to accelerate towards him the Earth will accelerate towards him at 1.22 times 10 to the negative 22nd. Sorry, that's 1.27. Oh, it's a little faster. Meters per second squared. That's a super, super small number, right? That's I can't even write that many zeros. The point of that exercise was just to show you the rate at which things accelerate towards the Earth and the rate at which the Earth accelerates towards things. Awesome. I want to do a little bit more with that in a moment, but for now, let's keep moving. So the next question says, what happens if the distance between two objects in space is doubled, tripled, quadrupled, blah? Let me show you that really quickly. Let's just say I doubled this distance. Double the distance. But notice since the r is squared, that 2 also has to be squared. So if I double the distance, I end up with 1/4 of the force. Because whatever you do to the right side must be done to the left side. And since the right side ends up being divided by 4, so must the left side. So if I double the distance, I get 1/4 of the force. And that's because 2 squared is 4. Let me hammer that home a bit by showing you what happens if I triple the distance. If I triple the distance, remember that 3 also has to be squared. 3 squared is 9, so if I triple it, I get 1/9 of the force. So the distance between the two objects and the force, so R and F, have what's called an inverse square proportionality. inverse square proportionality, which means whatever I do to the r, I have to do the inverse squared to f, and vice versa. If I double the r, then I have to do the inverse 1 over 2 squared 1 over 4 to the fourth. That makes sense? So this also shows you how quickly gravity drops off. Exponential. Because of that square there. And of course, just to hammer it home a little bit more, let's say I take 1/2 or I half the distance. Yeah, 1/2 r, but that's also in parentheses there. And so that's going to be 1 over squared, which equals 1 over 4. And so that means that this would multiply. Awesome. Any questions about that part? I'm talking about physics stuff now, so I'm pretty excited. I want to talk very briefly about how we describe motion. Just remember, a speed is a distance over time. And the only difference betwixt a speed and a velocity is that a velocity specifies direction. I'm going 50 miles per hour, okay? Which way? 50 miles per hour west. So velocity just specifies a direction. And so when we talk about an acceleration, which is a change in velocity, so if I'm at a stoplight and then it turns green and I accelerate up to, or I speed up to 60 miles per hour, I have accelerated. If I'm driving up to a stop sign and I got to slow down to stop, I have accelerated. If I'm going around a corner at 60 miles per hour and don't slow down, but my direction changes, I have still accelerated. So any change in velocity, whether it's your speed or your direction, I think we all had that. I just wanted to make sure and specify it. This slide here is just to talk a bit more about the acceleration due to Earth's gravity. And it says that objects near the Earth's surface, their velocity increases towards the center of the Earth at a rate of 9.8 meters per second for each second that they are falling towards the surface. So I want you to think a little bit about what an acceleration is. 9.8 meters per second, that's a velocity, and it increases by that amount each second that it's falling. Which means that if at time 0 and it has no velocity at that time, after 1 second, it should be going about 10 meters per second. 9.8. After 2 seconds, it should be going about 20 meters per second, and so on and so forth. But Mr. Palmer, what about terminal velocity? Terminal velocity is an effect of our atmosphere. So if we include our atmosphere, not only will these values be different due to air resistance, there would be some max speed that it could reach. Without an atmosphere, the max speed that something can accelerate to would be the speed of light. And I don't want to get too much into relativity, so I'll just leave that there. Okay. So one of the most interesting things that Galileo did was he demonstrated that the acceleration due to gravity should be the same for all things. And he demonstrated this mathematically. So, well, he also did experiments, but one of the ways he did it was mathematically. And I also want to do it mathematically. One of the reasons why we went to the moon was to confirm this, right? We had all types of math tests, but if you drop, I don't know, something really fluffy, a piece of paper and a brick, the brick's going to hit the ground first. Fluffy paper. Awesome. Yeah, the tennis ball hit the ground first, or hit the table first. So remember, if we're testing hypotheses and the hypothesis fails, then it's not correct and it needs to be fixed. But we were so sure that this hypothesis was correct, we're like, okay, what if there's other stuff involved, like air resistance? So we needed to be in a place where air doesn't exist. Here's the moon. All right, first, let's look at this mathematically, and then we'll go to the moon and test it. That's right, we're going to the moon in a video. First, let me throw some equations up here that we know about. We know that F equals ma again, and we know that the force of an object on another object equals, if we're talking about gravity, all right, now I want to do some clarifications. This big M represents the Earth. This little m, any object. Let's just say it's a cookie. And so this is going to be the force of gravity here. This force is also going to be the force of gravity. And this little m is also going to be that same cookie. All right, it's cookie. And this A is acceleration due to Earth's gravity. So we're going to call it G. But what you'll notice is that both of these are the force of gravity. Therefore, I can set them equal to each other. You may very quickly notice that the mass of the cookie is on both sides. Little m, little m. Mathematically, I can divide both sides by little m here. And it's still a true statement. And in this form, you can see that the acceleration due to Earth's gravity is without regard to whatever object it is it's accelerating. So the acceleration due to Earth's gravity should be constant for all objects if big M is much greater than little m. If we start talking about something that's on the scale of the mass of the Earth, it doesn't fall apart, but it's no longer as straightforward. But for any regular sized object, a car, a mountain, comet, please make sure you have this in your notes somewhere, because you're going to need this. If you think about this from the perspective of being true on Earth, this will help you on homework assignment number 4. because some of the questions say, find the acceleration due to gravity on Mars's surface, for instance. And I'm going to get these numbers wrong. It will say something like, Mars has a mass that's approximately 0.11 Earth masses and a radius that's about 0.5 Earth radius or something like that. And knowing that, you can find the answer to this question. I'll let you try to work the rest of it out on your own, but if you have questions about it in class one day, we'll work on that. All right, so let's go back to what we were focusing on now. Oh, perfect. Okay. We're about to go to the moon to confirm this mathematical hypothesis. But first I want to specify that Newton tied together the idea of forces with acceleration. So please remember that. If we see an acceleration of an object, there must be a force at play. This is a very fundamental concept in physics. If you slide down a hill, you're accelerating. Must be a force. All right. Any question on this page before we go to the moon really quickly? We're only going to be there for like, I don't know, 30 seconds. All right, hold your breath, everybody.
Well, in my left hand, I have a feather. In my right hand, a hammer. I guess one of the reasons we got here today was because of a gentleman named Galileo a long time ago, who made a rather significant discovery about falling objects in gravity fields. And we thought that where would be a better place to confirm his findings than on the moon. And so we thought we'd try it here for you. The feather happens to be appropriately a falcon feather for our falcon. And I'll drop the two of them here, and hopefully they'll hit the ground at the same time.
Awesome.
How about that?
Can you imagine how embarrassing that would have been if, like, the feather just, like, floated away or something? They're like, ugh. Bye, physics. Okay. I got one more video for us to look at. We'll talk a little bit more about it. There it is.
Have you wondered what it would be like to be an astronaut floating around in the space station? But why are the astronauts floating? I'm here at the Powerhouse Museum in Sydney to find out if anyone knows the answer. Why are they floating? No gravity.
No gravity.
Zero gravity.
There's no gravity.
The stuff that holds us to the planet when we spin doesn't have nothing.
Gravity holds you to the answer in space, there's nothing there. It's float.
There's no gravity in space.
No gravity, there's very little.
But is there really no gravity in space? After all, the moon orbits the Earth due to gravitational attraction. So, where would the space station fit in this picture?
Can you make me a roughly to scale model of the Earth and the Moon? And then we're going to position the space station in there. So run like that?
About there.
Are you ready to see the real distance? What do you reckon? Actually, about here. Maybe a little further. Now, if the moon is here and the Earth is there, whereabouts would you put the space station?
Oh, yeah.
50?
About halfway? Good. Right about here? So that's maybe like a quarter of the distance to the moon. Let me show you the real distance. Are you ready for the real distance? The space station is right about there.
Oh, okay,
Right
that's close.
there.
the space station is actually only about 400 kilometers away. So if you're in Sydney, it's a little further than the drive to Canberra. But does it make sense that the Earth exerts a big gravitational force on you, but nothing on the astronauts just a short distance away? You reckon there'd be no gravity there?
It's just how they float, we've seen them.
Well, clearly there's not. They're floating around.
I know they float. And the question is why?
No idea. I'm really confused.
Well, in truth, the force on the astronauts is almost as much as the force on you. So then, why are they floating while you're stuck here? The answer is the astronauts aren't floating, they're falling. Ah! And not only that, but the space station they're in is falling as well. Ah! So why doesn't the space station come crashing into the Earth? Well, the reason is the space station and astronauts inside have this huge sideways velocity of about 28,000 kilometers per hour. So even though they're falling towards the Earth, they're going so fast that as they fall towards the Earth's surface, it curves away from them.
If the Earth didn't put a gravitational force on them, they would fly out into space. Sure, yeah. Right. So it's due to that gravitational pull that they can actually keep orbiting the Earth.
If it was to stop moving, it would be plummeting.
Exactly.
But would they...
They would still feel weightless until you smash into something. So the space station and the astronauts inside are constantly accelerating towards the Earth's core, but they never get any closer. And because they're accelerating at the same rate, the astronauts feel weightless. They have this amazing sensation of floating.
That's super interesting. Okay, so just to make sure and specify, there is gravity in space. And as you can hopefully see by this equation here, its strength diminishes by r squared. However, no matter how large that r is, the value of F will never be 0. So there's gravity everywhere. There's always gravity somewhere. Or there is always gravity, excuse me. And so, like it says, the weightlessness that you're feeling is a state of being in constant free fall. You're falling towards the earth, you just keep missing forever and ever. So it's pretty interesting. I don't know. Would any of you all go into space? Anybody? I would go into space. I just don't want to have to get there. It's like the flight up there that I don't care for, because I don't like heights. But at that point, you're no longer really high. You're just, you're in orbit, so it doesn't matter. Another interesting thing about being in space is, so your inner ear fluid tells you where down is. So when you're standing still, it's resting on the base of your inner ear, which tells you down is that way. If you lean over here, it sloshes over a little bit. It tells you down is this way. However, if you're in space constantly falling, your inner ear fluid just kind of floats in the middle of your ear. So your sense of down is question mark. And if it touches any part of your inner ear, then down immediately becomes that direction. So let's just say you're like floating up against the wall and you push yourself off, your inner ear fluid's going to slosh to the front, so down becomes that direction. It sounds like it would be really nausea-inducing. I'd like to experience it, but it also seems really scary. This is just a slide explaining the universal law of gravitation, if you need that, so that it will be in your records. The next lecture, we're going to start talking about tides, because they relate directly to gravity. But that's going to be for the Thursday lecture. That is all for today. Thank you all very much. Have an excellent afternoon, morning, afternoon, whatever time of day it is. Yeah, that's why astronauts have to train so much to deal with nausea. And also they have to be in amazing shape because it's really physically demanding.